cryptography versus Kolmogorov complexity.
Okay, great. Yeah, thank you, Valentin, for the introduction. Yeah, so because Marco did this whole apology slide for not saying FCSP, then here is like an even bigger apology. And so they were going to focus on cryptography and the notion of Kolmogorov complexity. And yeah, no circuits will be used. Okay, so let's start. So, well, cryptography very important. It's everywhere. Fundamental infrastructure to secure our internet. And let me, starting by introducing the notion of private key, like encryption. And the problem here is, you want to send a message through a public channel, but you want your message to be still private. And how do you do it? So we have private key encryption where both parties share like a key, and decryption and encryption using the same key. And we also have a more advanced primitive called like public key encryption, where there's a public key and encryption uses a public key, but using the public key you cannot decrypt, and decryption only uses like a private key. So this enables private communication over public channels. And so what do we know? And so actually we know that private key encryption belongs to a huge class of private key primitives, including digital signature, web functions, authentication schemes, student generators, student functions, commitment schemes, zero knowledge, and coin tossing scheme, and so on. So this this is a class of this is called private key cryptography, and every primitive in this class, they are all equivalent. So you get construction of one thing, you get construction for all the other primitives in this class. And this is a private key cryptography, and they're kind of a weaker. So we also have a public key cryptography, which is stronger. And so today we're going to talk about the most basic public key primitive called key exchange. Key exchange protocol allows two parties who have never met before to agree on a secret key, and is crucial for building secure internet. And our internet is basically key exchange and a digital signature for authentication and private key encryption for privacy. And there are more advanced public key cryptography, including public key encryption, homomorphic encryption, MPC, oblivious transfer, and also IO. And we're not going to talk about those advanced things today. So great, we have those amazing, so many crypto primitives. But the question here is they are all being assumed. But do they really exist? But do secure cryptography really exist? And today, so we know that secure cryptography immediately implies that MP is not P2P. So today we're going to rely on a computational hardness assumption. And what's computational hardness assumption? So let me, the famous computational assumption is involves this integer factorization problem. So we're given a big integer, and the goal is to find p and q such that p times q equals this big integer. And this problem it seems to be hard for human, and the computational hardness assumption we need is this is also hard for computer. So there's no polynomial algorithm exists for computing factoring, and in fact this. So the integer factoring assumption belongs to a type a type of assumptions called number theoretical assumptions, and there are noisy linear algebra assumptions, and there are heuristic assumptions. So those are kind of three pillars supporting the foundation of cryptography. So what do we know about each pillar?
Classical.
Yeah. So we know for number theoretic assumptions, right? The classic cryptography, because we know if we have quantum computers, and then all these number theoretic assumptions will be broken, and factoring is easy. So there's a quantum polynomial time algorithm for doing integer factorization, and you also have algorithms for all these number theoretical based problems. So this pillar is kind of a crack that's shaking. So what do we know about noisy linear algebra based assumptions? And so these assumptions, for example, so like number theoretic assumptions, they're not post-quantum secure. And for noisy integer algebra assumptions, like the famous, so the situation here is like, you have like a system and the system is easy without noise. So you add like a small amount of noise, random noise, and it's like very small of like 0.1% magnitude. And the hope here is like, adding this noise, this problem becomes hard. And the famous example here is this like a LWE, learning with error problem, where essentially you are learning like an inner product of a secret vector, like with like a noise. And we know that, we have like a modern machine learning algorithms, such as like gradient descent. And they are like super robust with like dealing with noise. So you add, if you have like a machine learning gradient descent algorithm, you add like a tiny random noise, like a 1.1% noise. And it's not going to hurt anything, and the gradient descent still works. So, and we have like a machine, so for example, for LWE, we have like a machine learning attacks. And we don't know, like those machine learning algorithms are kind of evolving. So the second pillar here, they're not post-ML, post-machine learning, post-AI secure. Yes.
Have there been any actual machine learning attacks?
Yeah, let me introduce this line of work. So maybe I can say a little bit more about like learning with arrows. So here the problem is we are learning the inner product function of a secret vector with noise. So you're getting as many as data as you want. And you're trying to figure out the target function is just inner product. And you're getting examples like samples with noise. And this problem is easy without noise, is Gaussian elimination. And if it's easy if numbers are real numbers. It's called like a linear regression. And you can get like a simple like machine learning algorithm for it. So the trick here is, it's doing like a modular arithmetics, and it's doing over, the ring of like integers mod n, mod q. But there are still, machine learning attacks on them. And so basically here, like this is a state-of-art like model called like a transformer, and you can train your transformer to even dealing with like a arithmetic.
But transformers are really bad even at modular, unnoisy modular arithmetic.
Yeah, that's a good guess. So I think they kind of summarize. So let me.
I think you're inducing false panic at the moment. It may happen in the future. I don't think it's happened yet.
Yeah, let me mention this attack. So in their first paper, they kind of show the attack like a toy example of LWE. So this paper, they're not doing better than just brute force attack. And then, there's our follow-up works kind of handling like an intermediate LWE problem. Like they're not breaking, so it's not fully broken. They're not breaking those like LWE scheme like deployed in practice, but they're better than brute force. So they're breaking something with, say, they're breaking things where brute force algorithm takes like 2 to the 60 times, right? And then, maybe transformers are good at modular arithmetics, right? Because transformers you build, all this like ChatGPT and like large language model, and they think to be really good even as like reasoning. So yeah.
Okay.
Yeah, not okay. Yeah,
okay. I mean, like one reason why ChatGPT is getting better at these things is they add like specific linear algebra modules. They recognize when it's linear algebra and they go to a different algorithm at that point, right?
Yeah,
so it's not going to compose. So, okay, I don't think we have to panic yet. Okay, so it'd be nice to have.
Yeah, but it would be nice to have something post machine learning, right?
Yeah.
And any questions? Yeah, so let me continue. So current situation, so the number set construction is not post-quantum secure, but we don't have to be panicked because we don't have quantum computers yet, and the whole internet is still building on number set constructions. But would it be nice to have something post-quantum? And the same thing here, those machine learning attacks, they're not say breaking like LW, breaking linear, noisy linear algebra assumptions yet, but it would be nice to have something, post machine learning or post AI. And also let me mention like a last pillar, heuristic assumptions. And so here the situation is like, you develop some like a complicated scheme, and the hope for security is like, the scheme is like so complicated so that you hope the scheme is secure. But I want to mention, carefully designed schemes can still get broken. So we want, something that's not heuristic. So something, we want something that's like provably secure, post-quantum, and post-machine learning. So, but, we can't really prove it. So if we prove cryptography, say post-quantum, then we immediately prove like NPA is not QTP. So like a alternative way out is to, like.
But we have a week.
We have a week, yes. Yeah, so if we cannot prove NP is not QT in this week, alternative way out is to identify some master problem, whose hardness is also necessary. So hope here is you build cryptography from like a master problem, and hardness is also necessary. So if this construction gets broken, then every construction of cryptography also gets broken, and there's like no cryptography. So this is kind of the hope. And yeah, and then we know the answer to this question is like, Kolmogorov complexity is, the new pillar for supporting cryptography. And as we have seen like in the morning, like we have seen like this K capital T complexity, and we will introduce, this notion of time-bounded Kolmogorov complexity very soon. And yeah, people here all agree that it's a really important classic problem and has been studied since the 60s. So like really important problem. And we show that the existence of private key encryption is equivalent to time-bounded Kolmogorov complexity being hard on average. So the average case hardness, the notion we need here is like a standard notion of average case hardness, and it's kind of like a standard in computational complexity. And so this kind of, identifies like a master problem whose hardness characterizes the feasibility of, private key encryption and like all private key primitives such as like digital signatures and authentication schemes. Okay, so this is for private key encryption. And we also have a characterization for, the basic public key primitive secure key exchange. And we show that like the existence of secure key exchange is equivalent to, like the so-called interactive Kolmogorov complexity being like even worst case hard. And as I will like introduce later in this talk, this notion of like interactive Kolmogorov complexity is like a variant of Kolmogorov complexity that studies, like interactions, like protocols. It looks at, like a smallest program generating the transcript and output. And so here I want to mention that, those problems, those Kolmogorov complex problems, they're similarly unstructured. And there's no, for example, there's no algebraic structure in those problems. Like there's no integer, like addition, integer multiplication. And so this, then it's very likely for them to be, quantum safe and also ML safe. And as I mentioned, like if we have like a quantum algorithm breaking like our constructions, then there will be like no cryptography. And so yeah, not only sufficient but also necessary for cryptography. And any questions here? Okay, so let's move on. So today we're going to talk about like a private key primitives from Kolmogorov complexity. And we're going to talk about like how we construct the basic public key primitive key exchange protocol from Kolmogorov complexity. And in part 3, we'll talk about a little bit like new applications, theory, and practice. So let me start with introducing the notion of Kolmogorov complexity that we rely on. And yeah, so here let me introduce the notion of the classic notion of Kolmogorov complexity. And the motivating question here is, which of the following two strings is more random? because there are like individual strings and there's no distribution, no probability mass. And as suggested by Kolmogorov, so we can instead, look at the shortest length that's the shortest program that generates this string. And we can say for the first string, there's a very short Python program generating the string. And let me highlight here, right, the no-shell programs here. Yeah, it doesn't matter in this tutorial. We can just think of it as like a Python. Any universal Turing machine actually fits here. So, and let me mention, like short programs can not only generate like a trivial string like this, you can only get this like beautiful picture. This picture can be generated by like a very short program, but the picture is like beautiful picture kind of complicated. And so the notion of Kolmogorov complexity, it has a lot of amazing applications, such as we can prove like Gödel's incompleteness theorem using Kolmogorov complexity. We can prove density of primes using Kolmogorov complexity. But unfortunately, like this classical notion is like uncomputable, and uncomputable notions are typically not very interesting in computer science. So what do we do? So we instead of like look at arbitrary programs, we look at programs that are time bounded. So we fix like a runtime bound t. Think of t as like a function that t maps say like t of n equals n squared, and we let kt of x denotes like the same quantity, the length of the shortest program, with the restriction that the program is efficient and it will terminate within time t of length of x, like say length of x squared. And as you can see here, like t of x, this quantity becomes like efficiently computable. You can just enumerate all like small programs and run it in like within a certain amount of steps. But like the question we're going to look at here today is like, can kt be efficiently computed when the runtime bound t is a polynomial? And yeah, as mentioned before, this is a classic problem, and has been studied in the Soviet Union since the 60s. And it's like the oldest computational problem in computer science, even predates the theory of NP completeness. And whether this problem is NP hard, this is a major open problem in the field of matter complexity. And there is a long line of works focusing on whether this is NP hard. And we will touch this like later in this talk. And let me emphasize here that, unlike other problems from which we build cryptography, this problem has been resisting any attacks, like literally any attacks, for over 60 years. So improvement in the exponents of the brute force run, like exponents of the running time in the running time of the brute force algorithm. Like you just shave off like a little bit in the exponents of running time. This we don't know. Like this is best thing we know is like a brute force algorithm. Actually, there's a conjecture called like a pure conjecture. So basically says that the best way to compute kt complexity is to do this brute force algorithm. And let me mention that we do have non-trivial algorithms if you consider like a non-uniform algorithms. So if you consider like a non-uniform circuit or like an algorithm with like a huge like a preprocessed table, and actually the algorithm we get for computing kt complexity is kind of it's kind of inspired by like a cryptography, and we'll also kind of get to this like a non-usual algorithm later in this talk. Okay, then you might ask, yeah, it's a hard problem, it's a classical problem, but why do we study it? So what happens, if you have like efficient algorithm computing kt, and this is going to be a both slides. And let me mention, like optimal file compression is possible. So, right, like you have a file, you compute the shortest program, like generates your file, and that's your compression. And I'm going to, I'm going to claim that this is like a amazing, like a brilliant consequence if you can compute like time-bounded Kolmogorov complexity. And my claim is, science or like science discovery is easy. If you believe in this like a principle of Occam's razor, namely like the simplest explanation of phenomena is most likely the truest. Okay, so if you believe in Occam's razor, how do you do science in a world where KT is easy? Well, you collect data You collect data from the real world, you collect your observations, and you collect, sufficient metadata, and you compute like the shortest program that explains all the data. And if you believe in, the simplest explanation is the best, then this short program will tell you something. And, that's, you find the shortest program, and that's, this is something about like the truth of our nature in it. So yeah, so today we're going to, talk about hardness of KT. If it's hard, great, we'll be build cryptography. But if it's easy, yeah, that is also great news. Then we can have like a strong, like a powerful tool for scientific discovery. And let me mention that there's some caveats like collecting data or like collecting observation might be still hard, but still, right? But there's something in Kolmogorov complexity, like something like more interesting. And if it has an efficient algorithm, then great. Okay, so let me introduce, the notion of average case hardness we're going to rely on, and we're going to build, like a cryptography from this hardness. And in this average case hardness, it actually involves the frequential version of the problem and of computing Kolmogorov complexity. And it's also like a problem, has been asked, was asked in the 60s. And the problem here is, does there exist like an efficient algorithm that computes KT of X for a large fraction of X? So say, do I have an algorithm computing like a KT for a half fraction of strings, or do I have an algorithm computing KT for like a 99 fraction of strings? And here today, we're going to focus on, we define KT being mildly hard on average if morally there is a small fraction on which you cannot compute KT complexity. So how small is like a polynomial, like 1 over poly slice of all strings. So basically there exists a polynomial such that no polynomial time algorithm can compute KT complexity with probability 1 minus 1 over P of n over random strings. So you maybe succeed, with 99%. You maybe succeed with like, 1 minus 1 over n. But maybe there, as long as there, what I recall here is like there is a polynomial, maybe n squared, maybe like n to the 10, such that there's a slice, there's a like 1 over n cubed slice of strings on which your algorithm fell over random strings. And this holds for like infinitely many n. And this is going to be the average case hardness we rely on here. And questions? Okay. So we're going to show that KT being average case hard to compute is equivalent to the existence of private key encryption. And here, our focus here is going to be the basic primitive in cryptography called wire functions, which is in turn equivalent to private key encryption and digital signature and so on. So let me quickly introduce the notion of wire functions. So wire function basically F is like a one way. So more formally, we say that the function is one way if it's easy to compute. So it can be computed in polynomial time, and we say that it's hard to invert. So there's no polynomial time algorithm can invert it. And for example, here, if you have a random input x, remember wire function always takes a random input. And we require it's easy, this piece of Python code computes f of x in polynomial time. But given f of x, to find y, this is hard. This is going to take like, no polynomial time algorithm to find x, or even just find any free image of f of x. And the famous example of wire function candidate is the factoring problem. Actually, it should be like the multiplication function. So where we use the random input x to pick two large random primes p and q, and we simply output p times q. And if you believe in, factoring is hard, then this is one way. And as mentioned, we know that fireworks have shown that wire functions are both necessary and efficient for basically the world of public key primitives. And let me mention that we don't know how to build, for example, key exchange from private key encryptions or from private key primitives. And So, but here today we're going to look at, like here we're going to look at wire function, and wire function is the central primitive in cryptography. We're going to, construct a wire function from average case hardness of a computing KT complexity, and in fact, we show that this is also equivalent. So let me kind of next I'm going to sketch you like a little bit how we construct this wire function, and the other direction we're not going to talk about it in this tutorial. So let us say construct wire functions from KT being multi-Haldane average to compute. Okay, so we're going to construct a so-called like a weak wire function. So it's not going to be a full-fledged wire function, but we can transform it to a full-fledged wire function later. So let me sketch our weak wire function construction. So here we fix a constant C, such that for any string x, the KT complexity is at most length of x plus C. So if you think of like Python, then here C is just the length of the command print, and we're going to fix C to be this constant. Say like C is just maybe like 5, because print you only have like 5 letters, and so the input to our wire function. Remember, wire function is always takes like a random input. So basically, we're going to pick like a random things, and the input is like a random string pi prime of length like n plus c. And here, n, think of n is like an input length or like a security parameter, or it's like how large we want to run this function on. And we also take a random integer from 1 to 3 all the way to n plus c. Okay, so this is the input. It's like a string, random string pi prime of length n plus c, and an integer of like 1 to 3 all the way to n plus c. So this is our input. And step 1 is, well, we truncate this pi prime. So we take this random string, and we chop off the string. We only look at, we chop off it at position I. We only look at the first I bit. Okay, so like random string, you chop it off, and in step 2, what we do is like we take the first I bit pi, and we view it, we interpret it as a program, as say like the code of a piece of code, say like a piece of Python code, and we simply run this program pi for like t of n. Think of t as being like n squared. We're like running it for n squared step, and we get the output 1. So step 2, we take the truncation, we view it as a program, and we run it for like n squared steps, and we get the output, and the output is y. And finally, in step 3, we simply output, I, meaning like how long the program I run is, and also the output of the program y. So we output like I, comma, the output of the program y. So basically, the function, takes a random input, random string pi prime, and random location, random position I, and I chop off this random string to the first I bit. I run this, view it as a program, I run it, and I get the output, and an output, like the length of the program and the output of the program. So this is going to be our, we can't prove it's one way, but we'll prove it's like weakly one way, assuming average case hardness of KT complexity. And any questions about the construction of the weak wire function?
How should we think about this output? Like if it's still running?
Yes, if it's still running, we just cut it off. Then it's output like nothing or like false. So let me kind of briefly sketch, like, so how are we going to prove that it's a one way? So basically we assume for contradiction that it's not one way. Suppose for contradiction that some algorithm inverts it. And the question here is, and we want to use it in order to reach a contradiction, we want to use it to compute KT complexity of a random string. And if we can compute KT complexity of random string with high probability, and then we reach a contradiction. And kind of let me very sketchily, talk about how this reduction goes. So let's, for simplicity, think of, suppose it's not one way, then suppose there is somebody that inverts this function always. And suppose somebody inverts this function always with probability 1, and if we have a string x, and then we're going to compute the KT complexity of this string. Okay, so if you look at this function, so basically what you want to probably do is, you put your x at the outputs of the function, and you're trying to invert it, and like the question here is like you might get like an arbitrary program. You might not necessarily find like the shortest one. And here the trick here is like we use this index I or like the position I here. Okay, but algorithm, you try all possible I from like 1, 2, 3, 5 all the way to like n plus c, and you try to invert like 1 comma x, 2 comma x, 3 comma x. Maybe say at like 10 comma x, you're able to invert this function. And if you invert, right, then you're going to find a program of let's say 10. And this program is going to output like the string x. And you try all possible I from 1 all the way to n plus c, and you just pick the smallest I on which it succeeds. You pick the smallest I on which you find like a program that generates a string. So this is roughly how we compute KT complexity if we have an inverter. And any questions on this? Yes.
So you choose Y, so that's red box.
Yeah.
Uniformly at random instead of like choosing this input pi prime comma I.
Yeah, that's a good point, right? So here we're saying computing X over random inputs. And here, Y is going to be picked over random inputs. So note that if this algorithm succeeds with probability, if inverting succeeds with probability 1, then that's okay, right? Because then it inverts kind of any output you get. But for one functions, then the one function inverter, if you don't assume it succeeds with probability 1, then it only works on the distribution defined by of y defined by this one function. And so like in the formal proof, you need to work harder. So you basically need to show like so you basically need to show like a random input here. If it fits its uniform random string here, it also works with high probability. And that requires some work.
That is because a random pi prime comma I will get.
Yeah, the random pi prime will kind of output output of random program.
Oh, I see.
Yeah, so it's like different. It's not. Yeah, so great point. It's not the same as uniform random distribution. Like actually, it's very far from it. But in the real proof, like there's some more work, and you can show it actually works. Yeah, great question. Any other questions? Okay, great. So I'm kind of skipping all this proof. Okay, so here we just finished, how we construct private key primitives from Kolmogorov complexity, and let's briefly sketch how we construct the basic public key primitive, like the key exchange protocol, from the notion of Kolmogorov complexity. So let me start by introducing like the key exchange protocol, and key exchange, allows two parties who have never met before to agree on the same secret key. So it's going to be like a protocol, PA, PB, or it's like a two efficient algorithms. And so like in a protocol, there are two parties. So there is party A, and there is also party B. And so like a protocol for like these two parties is like, like you have two programs here, and they kind of exchange messages, and all those messages they exchange is called like a transcript, called like pi. And after you finish the protocol, then party A will receive an output X, party B will receive an output Y. And in order for it to become like a key exchange protocol, we require that two outputs are, they need to agree on the same key. So we require that X equals Y. And note that, well, the messages they are going to exchange are going to over the public channel. So for security, we require that, given the transcript, given the messages they exchanged, it's still computationally hard to find X or to find Y. Okay, so this is the notion of the key exchange protocol. And, let me mention that key exchange enables secure communication over the internet. So on the internet, like the first thing you do is like a key exchange, and then you agree on the same key, and then you run private key encryption to encrypt all your communications after that. So key exchange is a very important primitive securing our internet. And what do we know? So what are the current key exchange schemes? So let me mention that there's no heuristic construction for key exchange. So we don't know, key exchange scheme, we don't know like heuristic constructions. And the issue here is like, key exchange schemes only know it from like structured problems. So by structured problems, I mean like, for example, number theoretic problems, you have factoring, disk log, like they have this like a structure. No, it's linear algebra, that you're working with like a linear space and linear equations. So you also have like structure there. But like structure can be a good thing when you build like protocols, when you build cryptography, but it could be a bad thing, right? Because maybe you have an algorithm that exploits your structure, and from the structure, maybe there's somebody came up with like an efficient algorithm. And as said by the authors, so having structures kind of making those public key primitives endangered species, because they might just be wiped out by some algorithmic events. Okay, so like key exchange or public key cryptography, they only know it from like structured assumption. And the question here today is like, can we base key exchange protocol on some like unstructured computational harness? And the problem we're going to look at is the interactive Kolmogorov complexity problem. Okay, so let me kind of briefly introduce interactive Kolmogorov complexity problem. And let's recall, like the standard Kolmogorov complexity problem. And so here, KT of a string X is like, length of the shortest efficient program that's generated this string. Okay, so how about like interactive? Let's do like a first attempt, right? So maybe we can define like interactive Kolmogorov complexity IKT of a string X to be the length of, shortest efficient protocol that outputs X. So maybe this protocol and both parties get X as the output. And if you think about it, then this really doesn't capture, anything about interactive, because you can kind of show those things are the same thing. Because maybe, I can let one party just compute the string X and send it over to the other party and have its outputs. So this is not a great definition. And in order to capture interactive, like capture interaction. So here we're also adding, the transcripts into the, into the strings that we are interested in. So we define interactive Kolmogorov complexity over both, the outputs of the protocol and also the transcripts, the messages they exchange. So we define like the IKT of X comma pi to be the length of the shortest efficient protocol, such that, the output, if you run the protocol, both parties get X, and if the transcripts, like the message exchange, equals to pi. So basically now you can see now, right? Because if you fix the transcripts, then those parties, they have to kind of communicate according to the transcripts. And then you can always show like you can always show like those interaction can be simulated by like a single program, but the converse is not known. So like, because here like PA and PB, they might have like a private memories that the other party cannot read, and the transcript is kind of fixed. So this is going to be, like another notion. So yeah.
Is the protocol deterministic? I mean, is the randomness part of the description?
Yes, yes. So the protocol, like this protocol it's deterministic and no input, or meaning you hard code your inputs and your randomness into the protocol. Questions? So yeah, basically an interactive variance of Kolmogorov complexity, and we are looking for the smallest, the smallest efficient protocol that generates the transcripts and also the output. Okay, so this is roughly the interactive Kolmogorov complexity, and let me introduce, the IK problem that we're going to look at. So here we're given, two strings, like an output X and a transcript pi, and we're going to distinguish between the following two cases. So here, so in yes case, we have that the interactive Kolmogorov complexity time bounded of X and pi, it's like small. So in yes case, this small protocol such that when they interact, transcript is pi and the output is X. And in the no case, we have that the Kolmogorov complexity, the time unbounded Kolmogorov complexity is large. So basically, in the no case, we can say that even you consider like time unbounded program, even you don't restrict yourself with interaction, the complexity is still large. And so small was large, and what do we really mean by small? So here is like a relatively small. So like actually, so yes instance are X comma pi, whose IKT complexity is smaller than, relatively smaller than, the K complexity of the transcript, plus like a little bit, plus 10 log n, where like n here is like the length of the inputs. And the no instance is here, it's kind of also the same, is also relatively high. So the unbounded Kolmogorov complexity of like the output and the transcript is larger than the Kolmogorov complexity of pi, plus, it's a little bit more, like 50 log n. So what, yes?
Sorry, what's that?
And here you think of it like a length of the input, or like length of pi.
What's the length of pi or length of X?
Yeah, think of like pi and X are, equal length, and n is like length of pi. Yeah.
Now K of X here is the actual Kolmogorov complexity, not a time-bounded version?
Yeah, the actual Kolmogorov complexity.
Okay.
Yeah, so let me elaborate on it a little bit more. So here, yes case, basically says that, there's no additional cost to also generate X, right? Even interactively and efficiently. So basically says that if you look at, the widthness of the Kolmogorov complexity of pi, and so in order to, from this short program, in order to also generate X, like you don't have to pay much. So basically says that maybe, the best way to generate pi is interactive and also efficient. And here, like in no case, this is going to say that, this is a significant cost to also generate X. So basically, if you look at, if you view, the length, the length of the shortest program as like a cost, and here you, from the width, say the widthness of Kolmogorov complexity of pi, and in order to also generate X, you're going to pay more. You're going to pay like something. So basically says that pi itself just doesn't tell you how to generate X.
You're probably going to say, but how does it relate to conditional? Because what you're explaining sounds more and more conditional.
Yeah, it's kind of sounds very conditional, but here I guess the difference here is that in conditional we're thinking of given pi, and we're asking like given pi, how much do you need to pay in order to generate X? But here we're kind of looking at the widthness, like the small program that's generated pi.
Is IKT2 strings always upper bounded by IKT?
Yes, because you can always like simulate the interaction using like a single program, and right? So if you have a small protocol generating two strings, right, then you can write like a single program. So the KT complexity is always, smaller than the IKT complexity.
So interaction might make it harder to generate the strings?
Yes, because because in the interaction you no longer have like shared memories, and so basically you're kind of divided into two parties.
Probably you're going to say this, or you said it already. I understand that that's normal Kolmogorov complexity, not time bunch Kolmogorov complexity of pi. And intuitively, I'm trying to understand what this has to do with the obvious witness for like IKT x pi. There's not much additional cost to also generate x. Because I'm sort of scared that like, say I'm holding the witness to k of pi.
No, because you're never going to find the witness, right? So because in reality, you just you need to look at
So if I have like a small program generating X quickly, okay, and I look at and think of the transcript as the empty transcript, then one way of doing that is to just give the witness the sync description of X to both Alice and Bob.
yes,
Is that going to be IK complexity equal to the length of the witness or equal to twice the length of the witness?
twice.
Yes, that's going to be the subtlety that,
Yes,
so these things are within some constant factors of each other, but it's going to be important to get more precise.
yes.
Okay.
Yeah, thanks for the clarification, actually. Yeah, so let me repeat. So basically here, the IP complexity is defined to be the total length of both programs. So the length of a PA plus of the length of PB. So basically, to see why this is important, this is an example Russell just mentioned. Suppose you're looking at the IK complexity of, given the transcripts, say the transcript is like empty, and you want to look at IK complexity of the string X with the empty transcripts. In order to do this, you kind of have to copy, like the smallest program generating X like twice. And then, it's they're kind of within constant factor of each other, but it's important that, those small difference is going to be very important for us. Okay, so, yes.
This might come up later, but intuitively, why should I think of K here as opposed to like GT or something? Like what about K is going to be useful as opposed to like a time bounded KT on the right hand side?
Yeah, so you're asking if what happens if you change K to KT, or?
Yeah, I mean, like, I guess why are we?
I think like in principle, probably are going to do so, but okay, this time I'm not very sure, but I think if you consider K with a very large runtime bound, there's possible. Yeah, but yeah, good question.
Then you would change it in both places on the same month or on the second month for the node case.
Yeah, you're changing the node case, yeah. You're basically at the running time, but maybe like a much longer. Okay, so, yeah.
So the reason why you would have worst case bias here is it because you are defining a promise problem?
Yes. So this is a promise problem, and I promise you, like either it's this case or it's this case, and I just need to distinguish between this and this. Questions? Okay, great. So yeah, as you will probably guess, the hardness of this problem, the hardness of distinguishing like, relatively small and relatively high. So the notation here is, basically this RIKTP is this relative IKT problem. And if this is worst case hard, so if it's not a like infinite often promise BPP, then this is equivalent to the existence of key exchange problem. So this hardness of this problem equivalent to the existence of key exchange. So let me mention here, right? This is, the first stimuli unstructured. So there's no like a number theoretic structure, no algebraic structure, and this also characterizes the existence of key exchange. So any key exchange is cool will imply that this problem is hard, and if this problem is hard, we'll get a secure key exchange. Okay. So let me also mention that here we actually consider like a special case because we're considering protocols that generates the same output, right? And I denote this problem by like a RIKTP equal. And on the other hand, we can also consider like a more general version where you consider protocols having like different outputs, and you can basically also define the same problem. And the hardness of this problem, of general problem, this general version of the problem, is equivalent to wire function. So if you not only consider outputs that are same, you also consider different outputs, then the hardness of this problem is equivalent to the existence of one function. So the corollary here is like proving that one function implies the existence of key exchange is as easy as you build a reduction from like the general version of problem to the problem where we restrict ourselves to the equal outputs. And notice this is as easy as because this is equivalent to one function and this is equivalent to key exchange. So this is kind of like the sufficient and necessary thing you want to do. Okay. So yeah, let me go back to key exchange and let me briefly sketch like the construction of key exchange. So our construction of key exchange protocol from the IK problem. So here we're going to recall that the key exchange will have like two parties, and two parties want to agree on the same secret key. And the first step we're going to do is to let both parties sample random programs of random length. So we let party A to pick like a random length or like a random integer from 1 to 3 all the way to n. And party A samples a random program of length A. And party B also do the same thing. So party A has like random program PA, party B has random program PP. Okay, so first step 1 is sampling random program. And step 2, like we let the programs interact. So we view this program like programs PA/PB like as a protocol, and we let them exchange messages. We let them like interact. We let them communicate, and then they might send like messages back and forth. And then finally, like party A will receive an output X, and party B will receive the outputs Y. And yeah, of course, you do this only like a certain amount of time. Say this is determined by the running time bound in the IKT complexity. Okay, so step 3, because X and Y are kind of not necessarily equal to each other, so we're going to do like an equality check. So we'll let party A to sample like a random universal hash function, and we're going to send the hash function together with the hash values of its output X to the party B. And the party B will receive the hash values and the hash functions will, look at B's output Y and also compute hash values and check whether, the hash to the same value. And if so, party B will send back yes, and both parties will use, X and Y as the key. And if the hash value, is different, then they will just, use a bot or like using like a trivial key. So the key exchange protocol, step 1, you sample random programs of random length. And step 2, you let them interact for certain amount of steps. And step 3, you do like an equality check to check whether the outputs you get from, random programs are the same. And by doing so, by sending like hash values, and if they're same, we're happy and we use them as a key. If it's not same, we simply disable on. And so this is going to be the key exchange protocol. And any questions?
So, I'm sorry, I don't know anything about cryptography. Does key exchange only need to succeed with high probability?
Yeah, good points. I think there are, it's enough for them to succeed with a very high probability, or like one nice average fault.
So
but-
basically, if we accidentally, let's say that we're lucky enough that our random programs of random length actually agree on didn't agree on a key. But we found a collision in the hash function accidentally. That's like swept into the error term.
Yes,
Key
that's
exchange.
swapped to the like error term of the correctness.
Okay,
Yes.
thank you.
And as long as the correctness, is sufficiently large from, the security, you can always transform into like a standard key agreement where key exchange where, most with overwhelming probability, you have the same key and they're going to be secure.
But this is a lot like Levin's universal one-way function, right? Because you're kind of like guessing, you're hoping that A and B code a protocol that works with, that actually does secure key exchange, or you're diagonalizing against all, by picking at random, you have a constant, if there is such a protocol, you have a constant chance of guessing it.
Yeah, so
And then if you do that, then the rest will work.
so this is also like a universal key exchange protocol.
Yeah.
Yes, and I think the security rules, but I think there's kind of more than, maybe you don't have maybe this like a spectrum of things where, so with like a 11 universal construction, you get like definitely secure ones. And maybe they are, they are secure, not that secure. So I mean, that's kind of not like the only possibility. So what do I want to say? This is going to be universal, and on the other hand, we don't know how to turn like each universal key exchange protocol into, we don't know, but we kind of need this in order to compute this IKT complexity. We need like specifically this universal key exchange protocol. So if you have another universal key exchange protocol, we don't know how to use the integrator for that to computing the IK complexity problem. Yeah, so this is what I want to say. But yeah, this is this protocol will be universal, and we rely on it to get to get the key exchange from harness of interactive KT. And questions. Okay, so let me
Oh, what kind of, do you need like a universal one-way hash function or just pairwise independent?
just pairwise independent. Pretty much. Maybe I can quickly analyze it a bit. So basically, because we're doing like an inequality check at the end, so the probability that the outputs they disagree with each other is like tiny. So we have agreements for our key exchange protocol, and we want to prove like a security. So if so basically the transcript of our protocol is going to be like a transcript and a hash function and a hash value of the key, and whether it's equal or not. And we want to show that if somebody is able to do so, then we can decide this relative IKT complexity problem. And so in order to do so, in order to show like security, we're going to need a reduction. And now let's suppose we have a super strong adversary who can, given the transcript type and the hash function and hash values of the key, and, you know, 1-bit message. If from this thing, if we have an attacker that can always predict, that can always guess X. And we're going to use this like if to distinguish, you know, relative high KT, relative small KT, or relatively high KT. And so we're going to distinguish between like this. So this is like relatively low, and this is relatively high. So the idea here is basically we're going to trying to use like the if to guess. So we're given here an input, a transcript pi, and an output X. And so we want to know whether, you know, we need to pay more to pay, like we need to pay like little to also get X, or we need to pay very much to also get X. And here the idea is to, you know, we use the adversary to guess X. So we use the adversary to see how hard it is we are going to predict X from the transcript pi. So here we basically, you know, in the reduction, we sample a universal hash function. And because the input is like the transcript and output, we compute the hash of the outputs. And we send, you know, the whole thing, pi comma hash value, and 1-bit set it to be like equal success. And we send all the same to this adversary. And if the adversary is able to predict the output X, then we're saying that it has relatively small IKT complexity. And otherwise, we say that it has very high, like it has relatively high Kolmogorov complexity. So basically here is like, the thing here is like the hash value is like small. So if the adversary is able to predict X, so meaning kind of there is, you know, like you don't need to pay that much to also generate X. And if you have to pay a lot to also generate X, then it's impossible for Eve to predict X given only like 20 log bits of hash value. Yeah, so this is kind of roughly the reduction. So you use the attacker to see if there's a large cost to also generate your outputs. And if you succeed, then it kind of says that there's not much overhead. And if there is a large overhead, then you're never going to succeed. So yes.
What's the length of X?
Length of X is, think of it like n. Think of length of X equals like length of pi, and then all equals like n.
No, I'm saying in the key exchange protocol, like X and Y, what's the length?
Yeah, think of them as like n.
Then.
So like key exchange protocol, you know, like they could be small, they could be large, and they could be like empty. But we are kind of interested only when they, you know, have this outputs, and the output is like long enough and of length n.
Then why is it like non-negligible that they are the same? Because you want to get the same X equals Y after that.
Yeah, so basically you're going to have like a decent chance of agreeing on. I don't know. I have a better way to explain.
Is it obvious?
Well, take any protocol that,
Yeah.
you know, like take protocols that just like send X in the clear and output X.
Yeah.
Okay. So
You
that-
can have like silly protocols. Yeah. Russell said you send X, you know, in the clear in the message, and you just both print X.
Yeah.
And there are like a large fraction of protocols that would be like this. They don't necessarily have security, but there could be like many of them.
Yeah. And so if you fail the equality check, then you just keep on going, or you.
We just abort.
Yeah.
Yeah, and then but we rely on, you know, like application steps after this too.
Yeah.
So you will have those dummy key exchange situation.
Yes.
Where it's very easy to break.
Yes, but we'll show, you know, we're going to show there's a small chance, there's a decent chance on which you cannot break. And if that's true, we're going to amplify that to like a full-fledged key group protocol. So as long as you have the decent, like say 1 over poly chance of success, then that can be turned into like a full-fledged key agreement protocol.
Okay. So in the security game for the key exchange protocol, Eve succeeds on average
Yes.
over the programs.
Yes, yes, that's
You're
like a
going-
technicality we're going to deal with in the proof.
Okay.
Yeah. So here I'm just going to simply assume they works like 100%.
So can you explain the first thing again? Like just say what you said again,
Uh,
like the left-hand side, the if.
So if there's a huge cost to also generate X from pi, right? Then here if is trying to, if is trying to return X, guess X, but here we'll only pay, pay the length of hash values, which is like small. But here I guarantee you that in order to also generate X, you need like a 50 login bits. And it's kind of like more than what you get, and which basically says if it's this case, then EUV is almost never going to succeed. Okay, so this finishes our construction of key exchange from the interactive Kolmogorov complexity. And let me talk a little bit about, like theory and practice, new applications. So first, there is kind of a new perspective, like many new results on like computational complexity theory based on the connections between like Kolmogorov complexity, meta complexity to cryptography. And I want to mention here, like, the results of breaking the so-called like non-uniform Kilgore conjecture. So this is, work by like Noam, Rafael, and also Ryan, Rahul, and Shuish. So the statement is, there is, a non-trivial circuit, like a circuit of size 2 to the power of 4 and divided by 5. So it's like slightly smaller than 2 to the n. So it's like non-trivial circuits that's computing time-bounded Kolmogorov complexity of inputs of length n. So the theorem statement says that, like if we consider like non-uniform computation model, then there is a way to do like slightly better than brute force search. And the circuit size we need is like 2 to the 4n divided by 5. And so this, as mentioned, this is like shaving off like little bits in the exponent of running time, but it's only known in like non-uniform model. And okay, the proof idea is, as we just sketched, right? Like if we build a whatever function, then if we can invert this function, we're going to be able to compute the KT complexity of strings. And the good news to us is, there's a famous function inversion algorithm, like a fields and null. And then this is like a generic function inversion algorithm that's inverse like an arbitrary function. So, and basically we can apply like, the cryptographic algorithm of like inversing like a generic function inversion algorithm. And the caveat here is, we need to use like a circular version of it. So here, I think like fields now, they assume like a random access. So basically it's also known as like a time-space trade-off, where you prepare like a huge lookup table before your computation. And lookup table can be as long as like 2 to the, I think 2 to the 2n over 3. And so in the original algorithm, they assume like a random access to the lookup table. And in order to, make it like a circular version, you need like a circular version of this algorithm. But well, the idea is basically, if you can invert this one function just mentioned, you are able to compute KT complexity of string. And there is like a generic function inversion algorithm that's non-trivial, but so then we get a small circuit for computing time-bounded Kolmogorov complexity. So this is still that we know, and whether this is possible in the uniform computation model, we don't know, and so the pure conjecture for the uniform setting is, well, it still stands. So this is using like crypto ideas to resolve open problem in matter complexity. And another thing I want to mention is like, you know, the Kolmogorov complexity also provides us a way towards basing wave function, basing cryptography on the question of whether NP is not equal to P. So we know that existence of cryptography, existence of wave function, immediately implies NP is not equal to P. And whether the converse is true is the holy grail of cryptography. And if you look at this problem, well, it's related to, you know, K complexity, a new approach to, well, collapse impact as those 5 words. And okay, so let me kind of introduce, you know, like a impact those 5 words where we start from here. This is kind of where we live. And then we go from left to right, we make like more and more assumptions. And if we don't make any assumptions, we might live in algorithmic, where like NP is equal to P. So to go over algorithmic, like we assume like NP is not equal to P. And then there's a heuristic. Heuristic basically says, no, maybe NP is not equal to P, but NP is like hard on N. And to jump to, and then we assume NP is hard on average, then we got to like the so-called passive land. And here NP is hard on average, and we don't know whether wave function exists. So in order to get to mini-crypt, we need to additionally assume like wave functions. And you know, here in mini-crypt, we got all those like basic crypto primitives possible. And to move towards like cryptomania, this like, you know, stronger crypto assumption you need to assume. And so basically, whether you can kind of collapse or like you can exclude one of these words, or, you know, open like importance, open problems. And yeah, so let me kind of do like a brief survey of, you know, the K complexity approach. Okay, so basically basing wave functions on NP is not equal to P requires kind of you jump from algorithmic all the way to like a mini-crypt. And let's us first focus on maybe like a slightly less ambitious goal. Maybe let's first look at excluding passive lands. And so from what we have learned today, right? In order to exclude, so we show that wave functions is equivalent to average case hardness of computing KT. So in order to exclude impassivland, there are 2 things that we want to show. And the first thing, you know, is like computing KT is being NP hard. And so why this is useful, so suppose we want to show NP, we start with NP is hard on average. Then we get that there's exists a distribution over some NP complete problem, say over a set, on which this set is hard to compute over this distribution. And if we show KT is NP hard, then we get a distribution over, you know, KT complexities over strings on which computing KT complexity is hard. But we're not yet there yet. We're only saying, you know, the average case hardness over uniform distribution of KT is equivalent to wave function. So in step 2, we also need to show, you know, uniform distribution is like the hardest distribution. So we also need to show, you know, so here if we show KT is NP hard, then from NP is average case hard, we get a average case hard distribution over, you know, over strings for computing Kolmogorov complexity. And if we show the uniform distribution is the hardest distribution, then we end up with like, you know, hardness with respect to uniform distribution. And we get wave functions from the hardness of KT over uniform distribution. So those are kind of 2 things we would like to show. And the good news is that, you know, we still don't know with respect to NP hardness, but we know something about, say, you know, uniform distribution being hardest. So basically, we show that, you know, the following is true. So basically, we show that kind of uniform distribution is the hardest distribution, but with a caveat. We only show that, you know, if you have a distribution such as computing KT is hard for every polynomial T. So you have a single distribution, but computing KT for every polynomial T is hard. Then the uniform distribution for KT, computing KT is also hard. So we showed, uniform distribution is the hardest, but with the caveat that the distribution needs to consider all all time bound. Okay.
But
And then,
you also get the conclusion for all time bounds?
yes. And okay, great. So then we can kind of show then this, we have done this. And then next, it remains to show KT is NP hard star or a series. So star here means that we need to have a single reduction that's showing NP hardness for KT for every polynomial T. And you're kind of doing the same thing, and you are able to exclude epsilon. Okay, so star means that a single reduction works for every polynomial. But the issue is, this impossibility result, there's barriers. So basically says that such NP hardness star reduction, well, here we consider computing KT exactly. But if you're willing to consider just approximately computing KT with an additive factor of log n, omega log n, then there's no such a reduction. Either, unless NE equals co-NE or no derandomization. So, right, so basically, so here, the situation here is, so here, note that here we consider computing KT exactly, here we consider, approximately computing KT. Is this fundamental difference or just an artifact? Maybe this such a NP hardness star for KT, maybe it's also impossible. And now let's move on to consider, another notion called conditional Kolmogorov complexity. And conditional Kolmogorov complexity is, so basically you have a string X, but you also have auxiliary input Z, and you are asking, given Z, what's the smallest program to also generate X? Okay, so the hope here is, maybe considering KT, there's barriers, and maybe if we switch to conditional KT, maybe you can somehow, just get around of this barrier. Okay, so let's consider, conditional KT, and you can show, you can generalize LP20 to show that for conditional KT, still the same two things you want to show. You want to show, conditional KT is NP hard, and you want to show uniform distribution is a hardness, and then you combine with average case hardness of NP in the same way, and because the point here is a uniform distribution over conditional KT, average case hardness of that is also equivalent to one function. So still the same two things you want to show, and there are
Uniform is going to be on the input part, not the condition part.
both uniform over conditional parts and input part.
Okay.
Yeah, let's say both. Yeah. And okay, so what do we know? And actually, if you consider conditional Kolmogorov complexity, then there are two cases. So basically, whether case one is the surrounding time bound T is smaller than the length of auxiliary input. So here, case one, I'm not allowing the program to have to read the whole auxiliary input string, and the program is only have random access to the auxiliary input. And in this setting, we can show this is NP hard. And then in this setting, so we need to show uniform distribution is the hardest for or people call it a sublinear runtime bound. And for this, we we're stuck there, and we don't know how to make progress. And on the other hand, if we consider T that's polynomially larger than the auxiliary input, so if we consider the witness program that is able to read and maybe compute over the auxiliary input, then we can make progress on on the item B. So we can show that if we consider again an approximation variance of computing conditional KT, then we know that if you have a distribution such that approximating CKT is hard for all T, and this also implies wave functions. So basically, like I think you kind of have, so it's not really showing uniform is the hardest, but it kind of shows that any distribution for which this is hard for every polynomial implies the existence of wave function. So basically here we need to again prove this CKT like in the T larger than this of auxiliary input setting is NP hard. Okay, so if T is smaller than auxiliary input, we know it's NP hard, but we don't know whether uniform distribution is the hardest. And if we consider T polynomially larger than auxiliary input, then so the item B is kind of solved, but we need to show like approximating CKT is NP hard star. Okay, so what do we know? Yeah, so we just need to show approximates like conditional KT is NP hard star in this setting. So if we look at this approach, and good news is that we have no barriers, and in fact we know how to show approximating conditional Kolmogorov complexity. Like we know how to show it's NP hard, like even NP hard star, like even a single reduction that works for any runtime bounty. But the caveat here is like we only know it from super strong cryptographic assumption, such as like witness encryption or like obfuscation, from which you already rule out pestilence, and you even also rule out heuristica. So basically here is like, okay, yeah, this approach, there's no barrier, but we don't really know how to prove it without very strong cryptography. And cryptography that already implies the answer to the 5 worlds problem. Okay, and you may wonder, these cryptography schemes, they already not only exclude pestilence, but also exclude heuristica. And this is not coincidence, Like, in fact, such NP hardness star reduction, they exclude both heuristica and pestilence. So if you consider conditional Kolmogorov complexity, and you consider NP hardness star meaning that's a single reduction that works for every running time bounty, and then such NP hardness reduction directly rules out both heuristica and pestilence. And I want to mention that, if you consider NP hardness star with respect to, just standard version KT, it's also known that by work of Valiant and Haley, it's also known that they rule out both heuristica and pestilence. But standard Kolmogorov complexity is like impossible to get such NP hardness star reduction. Conditional Kolmogorov complexity, they are plausible, but they kind of, they rely on 2 strong assumptions. And the question here is, that maybe this is too much. And do we know wave function implies such NP hardness reduction? Are we assuming more? And in fact, I think, this is open problem to show like NP hardness star of approximating conditional KT assuming just wave functions. And so maybe stronger, but I think assuming random oracle, you are able to show this. So maybe this is a question with random oracle with wave function. And so like a result by Hirhana basically says that, okay, we don't know how to prove NP hardness star with conditional KT. But if we are willing to switch to distributional KT, then we know, like NP hardness, like star of the so-called like distributional KT is equivalent to a wave function. Why I put another star here? Because this reduction not only works for any runtime bound, but also works for any like efficiently computable oracle. So the sum restricts, but I think like the message here is that, for conditional KT, we don't know how to do it even from one function. And if we, would like to approach this 5 words problem, maybe consider distributional KT, but it's like an equivalence, but still, right? And let me mention that kind of all this approach you can by like a work of Shuish and Mikito, you can kind of all, you can have like a unified approach to showing, how to rule out like a heuristica and passive length. So both NP hardness reduction, I think each of them, they imply zero knowledge for NP. And you can use, their result says that zero knowledge for NP plus NP is not equal to P gives you one functions. So all those results kind of fall into the category of, you can interpret this as zero knowledge for NP, or zero knowledge for like the time-bound Kolmogorov complexity, or even zero knowledge for like any purity language. And the point here is, here like you need to show this NP hardness star. And if you think about it, it's a single reduction that works for every runtime bounty. It's kind, if some kind of cryptographic hardness is happening here, because you have a single reduction. And if you look at, the soundness of this reduction, it basically says that you're going to produce something that has high Kolmogorov capacity if the runtime bound is larger than your reduction. So you need some kind of cryptographic hardness here. And the question here, can we prove it without any hardness star? And so here we kind of introduce like new promise problems. And the worst case hardness of those promise problems will be equivalent to one functions. And this problem 1, I denoted as like, computational depth of KT. So it's basically says that we're computing KT complexity of string, but only restricting ourselves to, strings such that having the property that the KT complexity is not that big from the time unbounded K complexity of the string. So given that KT and K of X, they are, the difference is more computing KT, and we're also able to, to get this from the K complexity of this. We can also consider like a K poly complexity of this, but maybe with like a large polynomial time, like a polynomial runtime bounds. And we show that, worst case hardness of this, like restricted or like promise problems of KT, they can actually characterize the existence of one functions. So maybe we just need to show, instead of showing like a single reductions that works for every runtime bounds, maybe you can show, just like those like a conditional restricted problems are NP hard. But let me mention that well, still very challenged, even without, without promise, even just plain NP hardness for KT, like without this, it's still like a big open problem, and it's only known from random oracle. So still we haven't find something that's that doesn't imply one function in order to prove it. Okay, so this is kind of I'm also going to talk about the practical construction. I don't think I have time going over this. Yeah, so point here is whether we can deploy this Kolmogorov complex-based cryptography in practice, and there's some hope. And let me mention that I have a proof of concept implementation of like a PRG, and the runtime is like rather slow. It's like 0.1 seconds. It's probably like a 1,000 times or like a 10,000 times slower than the best like a PRG heuristic PRG construction. But maybe, but it's not something that's impossible. Maybe if you have very sensitive information, you have like a security is critical, then you might willing to pay a little price in efficiency, and this construction achieves like 128-bit security from minimum assumption. So yeah, time's up. So today, a new pillar for cryptography, we see private key encryption, key exchange, and theory and practice. Thank you.
How do you, analyze the security, of the private computation?
Yeah, good. So our practical equation is like provably secure. So we start with, we start with some assumption, which we think is like a minimal, but we plug in like a concrete like numbers into the assumption. And then we show, the security proof gives you like certain amount of security.
Don't you need those like n to be large enough for the assumptions?
Yes, but we need to, if you think about like a problem, there shouldn't be, the problem shouldn't be hard only after n equals like 10,000, right? Like if you don't have an algorithm, then it should be, maybe it should be hard when just as n is like decently large. So yes, as you said, we're never going to, sort of, yeah. So yeah, I agree with you that we're probably never going to, we're never going to kind of pin down a particular input length on which this problem is provably hard. And yeah, but I think in principle, I'm not really like worrying about it because yeah, so like naturally you shouldn't have an algorithm that stop working after n equals 1,000 or something like that.
But my feeling is if you take a random string of less than say 10,000 and you view it as a Python code, then with extremely high probability that is a wrong code.
Yes, good point. So like the choice of universal Turing machine here matters. And then like Python is no longer like a good choice here.
Okay, so you choose some other.
Yeah, we use just like the canonical representation of Turing machine. Like you use random string to generate like random transition function with, just.
Oh.
More questions? Thank you.
Right.
Right.